Okay, so I am now recording. Okay, so the solutions to homework 11 are on Blackboard. You can find them on Blackboard. There's an office hour tomorrow from 6:45 p.m. to 7:45 p.m. We can have a review after 10 p.m. tomorrow night if you want. Okay, so this lesson we finished the material for test 2 in the course. So we're up to 7.2.5, which is on conditional distributions. So x and y, let's say, are discrete random variables. Okay, so let's say the probability of x equals x naught, given that y equals y naught is equal to, okay, so it's equal to this probability. So it's the probability that x is equal to x naught, and y is equal to y naught, divided by the probability that y is equal to y naught. Okay, this is the conditional probability. This is the probability that x equals x naught, given that y equals y naught. So it's equal to in the numerator, the probability that x equals x naught and y equals y naught divided by the probability of y equals y naught. Another way to write this is f of x naught comma y naught. That's the value of the joint probability density function. And that's divided by f sub y of y naught. Okay, and so this is provided that the probability that y equals y naught is positive. Okay, provided that this thing you divide by in the definition is positive. Okay, now f sub x of x given y naught is equal to probability that x is equal to x, given that y is equal to y naught. Okay, so that's the probability x equals x given y equals y naught. That's equal to f of x comma y naught divided by f sub y of y naught. Okay, so it's the probability x equals x and y equals y naught divided by the probability y is equal to y naught. Okay, so this is the conditional probability function of capital X, given y is equal to y naught. So f sub x of x given y is equal to f of x comma y divided by f sub y of y. And this is if f sub y of y is positive for all x. F sub y of y given x is equal to f of x comma y divided by f sub x of x if f sub x of x is positive for all y, for all x. For all y. Because you're plugging in y here. Here you're plugging in x. Okay, so Yeah, because that's fixed. Okay, this is for both discrete and continuous random variables x and y. Okay. Okay, so this is the conditional probability of x given y equals y naught. It's probability. This is the probability x equals x given y equals y naught. And okay, and so we have these formulas. Okay. So let's look at examples. This is example 7.15. Let x and y be continuous random variables of a previous example, example 7.8. Okay, so for part A, the goal is going to be to compute f sub x of x. Okay, so example 7.8. This lesson. Okay, so example 7.8 was the following. Okay, so this is here. Okay, so here in this example, we let x and y be continuous random variables with this joint probability density function. Okay, so this tells you that so for any given value of any ordered tuple x comma y, f of x comma y is telling you the probability x equals little x and y equals capital Y equals little y. It's only non-zero in this region here, where x is between 0 and 1 and y is between 0 and 1. Okay, and let C be the points in the plane such that x plus y is less than 1, and so we found this probability. Okay, so that was that example. So now we're going to compute for this example f sub x of x. This is equal to the probability that x is equal to little x. Okay, so this is equal to the integral from negative infinity to infinity of f of x comma y dy. Okay, and so this is equal. There's two possibilities. Okay, so so you either have the integral of this thing when y is between 0 and 1. So when y is between 0 and 1, f is that, and otherwise it's 0. So here we're going to have the integral from 0 to 1 of this expression here, integrating over all possible values of y from 0 to 1. Oh, sorry, we're integrating with respect to x. No, it's with respect to y. Okay, good. Okay, so you integrate with respect to y, and then that's equal to x plus 1/2. And this is for 0 less than x less than 1. So remember, in order to find the probability x equals x, you're essentially adding the probabilities over all possible values of y of a fixed value of x. So if you fix capital X, you're fixing the value of x here. And you're essentially saying, what is the probability when, let's say, you always fix x equals 7. Say, what is the probability when x is 7 and y is 1, plus the probability when x is 7 and y is 2, plus the probability when x is 7 and y is 3, right? But instead of adding discretely, you're adding continuously, so you're integrating. So you're just integrating over all the possible values of y when you fix one value of x. And so that's the probability of the x being that one fixed value of x. And so you get this integral, which is equal to this. Remember, if you're integrating with respect to y, x is a constant, but that also means you're getting rid of y after you calculate it, right? And so all you're left with is an expression of x. So when you integrate with respect to y, x is constant. And so the answer is a constant, which is an expression of x, which is considered a constant because you're integrating with respect to y, okay? And so this is also 0 elsewhere. Okay, because otherwise the PDF f of x, y is 0, and you're integrating over 0, which is 0. Now f sub y of little y is equal to the integral, which is equal, this is equal to the probability that capital Y equals little y. It's equal to the integral from negative infinity to infinity. And remember, this is the opposite. So in order to find the probability capital Y equals little y, you're going to integrate. In this context, you're integrating with respect to x. You're adding up all the probabilities, fixing the value of y. You're in a sense adding as you're changing the values of x. Okay, so now there's two possibilities. So again, either the PF is 0 or it's not 0, right? So if it's non-zero, PF is non-zero, then we're talking about y between 0 and 1. If y is between 0 and 1, if y is between 0 and 1, then this PDF is non-zero. So you're integrating over this, which is non-zero. If y isn't in this interval, then PDF is 0. And so you have this PDF when y is between 0 and 1. And you're going to integrate that PDF, but you're integrating over the whole real line, but it's only non-zero between 0 and 1 for y. And so that means you only have to integrate it between 0 and 1. Well, so you're integrating over x. So here, see these x's. Only between x between 0 and 1 is this PDF non-zero. And so when you choose y's in this interval, you have to also choose x's in this interval to make it non-zero. So when you choose a value of y between 0 and 1, you integrate over all of x, which boils down to integrating from 0 to 1. Okay. And so this is equal to y plus 3/2 y squared. And this is for 0 less than y less than 1. And then this is 0 elsewhere. Okay, so if you choose a y between 0 and 1, then that means that the PDF is non-zero. But now you integrate over all of x. And so when you integrate over all of x, you're only integrating from 0 to 1 because the PDF is also 0 when x is not 0 between 0 and 1. And so you get this integral over all of r, which boils down to just between 0 and 1 with respect to x. You get this for those y's and for everything else at 0. Okay, so you have to think about that. Okay, so for part B, let's say for 0 less than y less than 1, let's look at f sub x given y. This is equal to probably x equals x and y equals y of f sub y of y, which is equal to, okay, so again, the PDF is only, so you're fixing a y between 0 and 1. And so for that y you're fixing between 0 and 1, you're considering values of x. And so there's two possibilities. Either you're going to have an x value between 0 and 1, or you don't, in which case the PDF is 0. Okay, but if x is between 0 and 1, then that means that the value of f of x, y over that is equal to the fraction where in the numerator you have this, right? So in the numerator you have f of x comma y, which we said over here was this. And this is for these intervals here, right? And so that means here you get f as that. Now f sub y of y, we found if y is between 0 and 1 for these values of y, we found that f sub y of y is equal to that. And so you substitute. And so you get that divided by that for x between 0 and 1 and 0 elsewhere. For 0 less than x less than 1, if you take f sub y of x given y, then this is equal to f of x comma y divided by f sub x of x. And so this is equal to, again, there's two possibilities. So if you fix x between 0 and 1, then what you need to do is you need to consider only y values between 0 and 1 in order for this PDF to be non-zero. And so if that happens, that means the numerator in this possibility, this is if, or this is for 0 less than y less than 1. And so for those y's, this numerator is that. And the denominator, f sub x of x, is for x between 0 and 1, which is what we're considering here. For those x's, we have this expression, x plus 1/2. And so now you just plug in again, you plug in x plus 1/2 there. So this divided by that for those values of y is the value of this, assuming x is between 0 and 1 fixed. Otherwise, it's 0. That's because the PDF is 0 everywhere else. The numerator would be 0 anywhere else. Okay. Any y is outside of this interval given x in that interval. Okay, so part B, we find both of those, f sub x given y and f sub y x given y. This was the blue part here, right? I was highlighting that part there. And then this here is the denominator, right? But so this is this, right? So in the same thing here, you're just plugging in this value for where you're looking at. And then you're plugging this value for where you're looking at, right? You're plugging this for where you're looking at, and this for where you're looking at. Okay, from what we did in B, from what we did in A, okay? And the given. So the probability that 0 is less than or equal to x, less than or equal to 0.5, is equal to the integral as x goes from 0 to 0.5 of f sub x of x, which is the probability capital X equals little x. Yes, you're just integrating over that from 0 to 0.5. And so to integrate this, you're integrating from 0 to 0.5. From 0 to 0.5, f of sub x of x, this function, from x between 0 and 0.5 is x plus 1/2. So that means you plug in the PDF here. You plug in f sub x of x there. Okay? And so when you calculate that, you get 0.375. Must equal to 0.4, which is equal to the interval from 0 to 0.4 of f sub y of y. Okay, so now you just plug this in. Okay, so now you just plug this in there. So f sub y of y, when y is between 0 and 0.4, is equal to y plus 3/2 y squared. So I'm plugging that in here. And so then this is equal to, and so when you calculate that, you get 0.112. Okay, in part D, let's find the probability that 0 is less than or equal to x less than or equal to 0.5, given that y is equal to 0.3. Okay, and so this is equal to the integral from 0 to 0.5 of little f of x given 0.3 at y is equal to 0.3 dx. And so this is equal to, so you're integrating that from 0 to 5, 0 to 0.5. So it's from 0 to 0.5, from 0 to 1/2 of f sub x given f sub x f of x, oh, yeah, f sub x. Okay, so it's f sub x given 3. Okay, so given 0.3. So we want the value of this to plug in here. So this is the same as f of x comma y divided by f sub x of x. Okay, but here y is 0.3, so you want a 0.3 there. Okay, and we put it 0 there, so it's more visible. Okay, so I'm gonna zoom in. Okay, so so this is equal, right? F sub x given 0.3 is equal to f of x comma 0.3 divided by f sub x. Okay, so f of x comma 0.3. So f of x comma 0.3, you just plug in y equals 0.3 there. Okay, and so you get 2x times 0.3 plus 3/2 times 0.3 squared divided by, then plugging in f sub x of x, and f sub x of x is this expression. Oh, here we go. Okay, we just have it right here. Well, let's just use it right here. We have f sub x of x given y, which is here, right? And so it is that, but you can just plug in y is equal to 0.3 here. So let's not rewrite that step. So you're using this value here. Okay. You're plugging in this thing, except y is 0.3. Okay, so this thing is 0.3. Okay. And so that is 0.3. And so now you're integrating with respect to x. And so when you integrate that with respect to x after plugging in y into that expression, you get that this is equal to 0.3276. Okay, so that's calculating an integral, and you calculate it and you get that number. That's D. Okay, so this section is annoying, but this is a good example with regards to seeing all the different functions involved. So in each of these sections, you're seeing the functions and you're seeing them calculated. So this is a good example to go over to know this stuff. Okay, so then the probability of 0 less or equal to y less or equal to 0.4, given that x is equal to 0.2, is equal to the integral from 0 to 0.4 of f sub y of y given 0.2 d y. Okay, and so now here, this is equal to, so you want to calculate this integral, but we have f sub y of y given 0.2. So f sub y of oh, okay, this is a typo. It should be y given x there. Okay. Okay, that should just be switched there. Okay, so these are the values of y. This is the value of x because it's f sub y, so this is the value of y. This is f sub x, so this is x, and then that's y. Okay, that's the condition. Okay, so f sub y of y given 0.2. You're just plugging in x equals 0.2 into there. So it's this expression when x is 0.2. Okay, so you take this expression, you plug it in for here, but x is going to be 0.2. So here is a 0.2. Okay, this is also a 0.2. And now you have an expression of y, and you integrate it from 0 to 0.4, and you get 0.0914. Okay, so we broke the problem down to calculating an integral. And you calculate and you get that number. Okay, so this is an example covering all those functions. Bless you. So next is 7.2.6, the multinomial distribution. Okay, so let n and k be positive integers. Let p1 to p sub k be the numbers such that the sum from I equals 1 to k of p sub I is equal to 1. And each of the pi's are between 0 and 1 inclusive. This is for I from, well, I. So from I from 1 to k. So the multinomial probability function, little f, is defined by the following. F of x1, x2, comma, comma, x sub k is equal to n factorial divided by x1 factorial, x2 factorial, n sub k factorial times p1 to the x1 times p2 p1 to the x1 times p2 to the x2 times p sub k x k. Here's x1 x sub k are equal to 0, such that the sum of the p's is 1. Some of the some of the x's, sorry, some of the x's is n. Okay, so this is the multinomial probability function. As this PDF, these are integers, x1 to xk, and the sum of them is equal to n. Okay, the sum of the pi's, which are the probabilities, add up to 1. Okay, so let's say, for instance, you have the probability that there are exactly x sub I occurrences of outcome a sub I for I from 1 to k. This is equal to the probability that x1 is equal to little x1. x2 is equal to little x2. Dot. X sub k is equal to x little x sub k. And this is equal to this. Okay, so the probability of x sub I occurrences of an outcome a sub I for each of the i's from 1 to k is the probability that x1 equals little x1, x2 equals little x2, xk equals little xk. And so it's equal to, you take each probability for each x, capital X, raise it to the power of how many occurrences each one has, but then you're multiplying by n factorial divided by those product of factorials, and it's just the number of ways to choose this many occurrences of each of them. So, well, it's just number of orderings of them, right? So you can rearrange the orders of these occurrences, right? This product is as if you ordered them in one way, but then there's this many ways to arrange each of these occurrences of each outcome, and each of them have that probability. So you have to multiply by how many ways you can arrange having xi occurrences for each ai. Okay. Okay, so this is the number of arrangements of those xi occurrences for each outcome ai. So if there are two outcomes, if there's a1 and a2, right, and you had one occurrence of each, then you have, let's say, a1 first and a2 next. There'd be a probability for a1 first and a2 next. But then there could be the probability of a2 first and a1 next, right? So then this fraction would take into account how many ways you can rearrange this many occurrences for each outcome ai, and so you'd have to multiply. Okay. So you have 7.2.7, which is the bivariate normal distribution. So this definition 7.7. Let mu1, comma mu2, sigma 1, sigma 2, and p be constants with sigma 1 positive, sigma 2 positive, and -1 less than p less than 1. The function f of x comma y, which is equal to this, e to the -1 divided by 2 times 1 minus e squared times x minus mu 1 divided x minus mu 1 divided by sigma 1. Okay. Squared minus 2p times x minus mu 1 over sigma 1 x minus mu 2 over sigma 2 plus sorry, this is a y, but y minus mu 2 over sigma 2 plus y minus mu2 over sigma 2 squared. Write it like that. Squared. All of that divided by 2 pi sigma 1 sigma 2 times the square root of 1 minus p squared. That whole thing. For negative infinity less than x, where both x and y are finite numbers. That's what I mean. Is the bivariate normal probability density function, the bivariate PDF. Okay, so it's another probability density function. Okay, you do not have to memorize that. Okay, so do not memorize, or do not memorize. You do not have to memorize. I'm telling you, you could if you want. You don't have to. Okay. Okay, so the next section is 7.3. It's on independent random variables. Okay, so we're almost done. 7.3.1 is on the definition of independent random variables. Definition 7.8. So we're going to let x1, xn be random variables, discrete or continuous. With probability functions f1 of x, comma dot dot dot, comma f sub n x n. So this is x1, taking that little x1 is values of capital X1 dot dot dot, little xn is values of capital Xn, respectively. And multivariate probability function f of x1 comma dot 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 comma x n. The n random variables are independent if f of x1 comma dot 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 comma x sub n is equal to f1 of x1 times f2 of x2 times dot 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 f sub n of x n. Okay, so the n random variables x1, xn are independent if you can think of the value of the multivariate probability function as being a product of the separate probability functions from f1 to fn. And that's for all values. For all values of x1 to xn of capital X1 to capital Xn, respectively. Except at all points of discontinuity, in which case you don't need that equation to hold there. Okay, so example 7.17. Let x1 equal to the value on a die. Let x2 equal to the number of heads from one coin flip. Okay, so either 1 or 0, right? If it's heads, it's 1. If it's tails, 0. F sub 1 of x1 is equal to the probability that x1 is equal to little x1. And so this is equal to 1/6 for x1, any of the values from 1 to 3. It's 1 to 6, right? The probability that capital X1 takes on any of the values from 1 to 6 is 1/6. and f sub 2 and f sub 2 of x2, well, it's flipping a coin, right? This is the probability that capital X2 is equal to some fixed little x2. And this is equal to 1/2 for x2 is equal to 0 or 1. It's a 1/2 chance that when you flip a coin once, you get 0 heads. And there's a 1/2 chance you get 1 head. So f of x1, comma x2 is equal to, well, flipping a coin, rolling a die and flipping a coin are two independent events, right? So with the fact that rolling a die and flipping a coin are two independent, that rolling a die and recording number on the top face of the die and flipping a coin and recording the number of heads are two independent random variables, right? And so that means that you can think of this as f1 of x1 is f2 of x2. And so this is equal to now 1/6 times 1/2, right? This is 1/6 for that one and 1/2 for the next one. So that product is equal to 1/12. And this is for x, all values of x1, x2. So this is for x1 is equal to 1, 2, 3, 4, 5, and 6. And x2 is equal to 0, 1. Okay, so all possible values of x1 and x2. Oh, oops, I'm sorry. Wait. For a second. Okay, so forget this is the reason. Just if you were to find the probabilities of rolling a die a certain number and getting a certain number of heads, right? For each of them, you would get the probability is equal to 1/12. Okay. Okay. So start over again. So each of these probabilities is 1/12. Separately, you find that f sub 1 of x1 times f sub 2 of x2, that's equal to 1/6 times 1/2. That's equal to 1/12. This is for x1 equaling to 1, 2, 3, 4, 5, or 6. x2 is equal to 0, 1, right? So separately, you find this product is equal to this, right? It's the same as this. And so this is equal to this. Okay, so we get that f of x1 comma x2 is equal to f sub 1 of x1 times f sub 2 of x2. Okay, and so that implies that x1 and x2 are independent random variables. Okay, the fact that you calculate each of these separately and they're the same, they're equal, and this is for all x1, x2. Okay. And so that implies x1, capital X1, capital X2 are independent random variables. Okay, so now you can conclude that way. Okay, so here we have if you have x1 and x2 are independent, and that A, in a sense, the event A, and the event A is capital X1. The event A is capital X1 is equal to little x1. Okay, and you have that capital B is equal to the event of capital X2 is equal to little x2. So this is events. These are events A and B. Okay, then all of that. So those three things imply, sorry, are equivalent to. Well, that is equivalent to the probability of A intersect B. B is equal to P of A times P of B. Okay. So these two are equivalent. Given that event A is this and event B is that, saying the probability that both x1 equals x1 and x2 equals x2 is equal to the product of those probabilities if and only if x1 and x2 are independent. So this is kind of just a restatement. Well, it's going back. It's saying that these two are equivalent. Okay, if you know one, then you know the other. Okay. One more thing, and then the material is done. 7.3.3 on independence, random variables derived from independent experiments. Part A, the capital E equal an experiment. Capital S equals sample space for that experiment E. I'll let capital X equal to a random variable on capital S, on sample space capital S. E is repeated n times under identical conditions. The random variables x1 to xn are independent random variables if x sub I is equal to the random variable on the ith performance of E from 1 less than I less than n. Okay, so if you repeat an experiment n times and x1 to xn are the random variables for the ith performance of that experiment E. So if you perform the experiment 10 times under identical conditions, then each time you perform it, you have a separate random variable for performing that experiment. Okay, and so all those random variables from the first time you perform the experiment to the last nth time, together they're independent random variables. Okay, and part B, if you have E1 to En, and that they are separate and distinct experiments. Okay, so before we had the identical experiment repeated over and over again. Here we have separate and distinct experiments. The outcome of E sub I is no way dependent on the outcome for any E sub j when I is not equal to j. So if you perform n experiments that are separate and distinct, but it's saying the outcome of any one of them is in no way dependent on the outcomes of any of the other experiments, different from that itself. And if you take S1, Sn, these are all assumptions. You take S1 to Sn, and you say that they are sample spaces for E1 to En, respectively. Okay, so you assume that also if x, if x1, xn are random variables defined on S1, Sn, respectively, then they are also independent random variables. Okay, so in A and B, it gives you situations where you know you have independent random variables. Okay, so if A happens or B happens, then your x1 to xn's are independent random variables. Okay, so that's what I'm going to write here. If x1 to xn satisfy A or B, then they are independent by definition 7.8. Okay, and this is the end of Math 241 material. Okay, so we've now finished the material, though we have to move. We still have to keep going. So we have a test, right, on Thursday. So I'm assigning homework 11 for this material, and I have the solutions on Blackboard. And like I said, there's an office hour tomorrow. And so if you need help with that homework, you should do it well tonight or tomorrow, early tomorrow. The office hour is late tomorrow. And so you can ask me questions about it. But now we'll have a review for test for the next test, okay? Review for test 2 now. Okay, does anyone have questions they want me to go over? There's the practice problems.
Professor.
Yeah.
Could you go over the practice problems? I think it was number 7, or yeah, number 7.
Sure. Okay. So so let's look at number 7. I see on the chat for number 6 also. Okay. So you should see on the screen. You should see the practice questions here. So for number 7, consider this experiment. Roll a die. If the outcome is a 4, select a number at random from the interval from 0 to 2. If the outcome is not a 4, select a number at random from 2 to 3. Let x equal the value of the number selected. Draw a histogram for this random variable, assuming x is rounded to 1 decimal place. Okay, so so there's 2 possibilities, right? If you roll a 4, you select a number from 0 to 2. Maybe I can draw this here at the bottom. Okay, so we have from 0 to 2, and we have from 2 to 3. Okay, actually, I need more space here. It's probably better if I move this over a little bit, as much as possible. So let's say this was 1 here. Oh, at the end, this was 2. Oh, it's 0 to 2. Okay, I'm wasting time here. So it's from 0 to 2, and then 2 to 3. So 0 to 2, and 2 to 3. Okay, so if the outcome, so if the outcome is a 4, you choose it from interval from 0 to 2. The probability of rolling a 4 is 1/6, because there's 6 numbers on a die, right? You roll a standard 6-sided die. The probability of rolling a 4 is 1/6. So you could choose any of these numbers. So you're rounding to 1 decimal place. So if you're rounding 1 decimal place, you have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 0.9, and 2. Now, if you roll 1/6, right? If you look at the numbers in between, right? You could have 1, 0.5. You could have 1.5, right? So it goes up like that. Okay, so 1/10. If you were to round to one of these decimal points in the middle, like if you were going to round to 0.5, you would have to look at half of a tenth less and half of a tenth more. That would be this interval here would have length 0.1, because it'd be half of a tenth to the left, half a tenth to the right. That would round to that nearest tenth. So that's 0.1 out of the total 2 space. So that makes up 1/20th total space. And so there's a 1/6 chance you would roll a 4, which means you choose a number from 0 to 2, and there's a 1/20th% chance that you would randomly choose a number inside that small interval. So this is 1 over 120. So the probability that you would round to 0.5 in this situation would be 1 over 120. Okay, the picture may not be drawn to scale just to make things easier. Okay, so the heights are good. So now you have, okay, so you have this height of the bar for each of the tenths here. So you have 0.1, 0.2, 0.3, 0.4. You get it? So then you have these bars, right, above each of the tenths. Those are vertical lines, okay? And they're in between the intervals. So I'm centering these bars at the 0.1s, okay? So now you have, it's not on the blue lines, it's in between them. Okay, so now each of those bars represent the height of the bar for each one is representing the probability that you would choose a number between 0 and 2 after rolling 1/6, and then you would randomly select a number in a 1/10 interval that would round to one of those nearest numbers. Okay, now the probability that you would round to 0 would be, well, there's half of a tenth. So there's half of a tenth. And so the space and the number line from 0 to 2 that would round down to 0 is 1 over 40. So there's a 1/6 chance of rolling a 4, and then there's a 1/40th chance that you would randomly select a number from 0 to 2 that would round down to 0. And so this is 1 over 240. It's just half that probability. And so now this probability, the height of this bar for 0 would be 1 over 240. Okay, so that's the probability of rounding up to 0. There's also 1 over 240 chance you would round up to 2. But there's also a chance you would round down to 2 if you choose a number between 2 and 3. So we have to consider that. Now, from 2 to 3, right, you could have 2.5. You could have 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, and 2.9, right? Each of those. Now, in order to get a number from 2 to 3, you would have to not roll a 4. So there's a 5/6 chance of not rolling a 4. And then after you don't roll a 4, there's a 1/10 interval that would round to one of these tenths, either half of a tenth less or half of a tenth more. So that's 1/10 of the length of the interval from 2 to 3. And so 5 over 10 is 1/2. So this is 1/12. So the probability of rounding to one of these tenths would be 1/12, which is much bigger than 1 over 120. And so this is 1/12. Okay. And so now that's the probabilities for these. From 2.1 to 2.9. Each of those would round to be a 1/10 of the interval that would round to one of those. Okay, that's a vertical line. Yeah, so I'm just drawing vertical lines here, one in between each one to represent the probability of each of those bars. Okay, so now what is the probability that you would round to 2? Well, there's a 1 over 240 chance you would round up to 2, and there's a 1/12 chance you would round. Oh, sorry. So the 1/12 here, right? That's for one of these 1/10s. Now, if you want to roll, let's say you round up to a 3. There's a 5/6 chance you choose a number between 2 and 3. Then to round up to 3, you would have to be between 2.95 and 3. So that's 1/20th of the space between 2 and 3. And so this is 1 over 24. So there's a 1 over 24 chance you would round up to 3. That's half of the 1/12 chance. So there's a 1 over 24 chance that you would round up. It's going to be half of that bar. Okay, so then there'd be that. And the bar is centered at the number. It doesn't represent the numbers that are rounding to it. So this bar is going past 3, but we're only thinking of the numbers below 3 rounding up to 3. And then to round to 2, you can either round up to 2, which has a 1 over 240 chance, which is the same as probability of rounding down to 0, or what the probability rounding up to 3 is the same as the probability rounding down to 2, which is 1 over 24. So 1 over 240 plus 1 over 24 is equal to 11 over 240. So that's 11 over 240. And so that's a little bit more than 1 over 24. And so you have this probability, which is 11 over 240. And so that probability is the height of it at 2. Okay, and so there you go. Does that answer your question?
Yes.
Okay, so what you're doing is you're then finding the probability. The heights of the histogram correspond with part B. You'd write down the probability for each tenth. So you would have, f of x is equal to 1 over 120 if x is equal to 0.1, 0.2, 0.3, 0.4, 0.5, dot, 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 0.1.9, right? And you would just separate it like that as a piecewise function. Okay, so that's number 7. So someone else also asked about number 6. Let x be a continuous random variable with the PDF f of x is equal to that. Find e of x. Okay, so to find e of x, you just want to integrate that. So let me do this on the on Word. So x is a continuous random variable with that PDF, and we want to find e of x. Okay, so number 7 is on the video. Okay, number 6, that's our PDF, right? So it's beta e to negative beta x. So it's beta e to the negative beta x. It's beta e to the negative beta x. If x is greater than or equal to 0 and 0 elsewhere. Okay, that's our PDF function. We want to find e of x. Okay, so e of x. So for e of x, we just want to integrate from, well, it would be from negative infinity to infinity, right? That's it you can start off with, of your PDF function f of x dx. But we see that this PDF f of x is only non-zero for x greater than or equal to 0. And so we can restrict where we're integrating for just 0 to infinity, all the x values that are greater than or equal to 0, right? And the PDF there, f of x, is this, dx. And so you integrate that. Okay, so to integrate that, you can take u substitution. Okay, so you can use u substitution to calculate the above integral. Let u equal to, let's say, negative beta x. Then du is equal to negative beta dx. And we get that the above equals, okay, so now we're going to get the above equals, so we use u substitution, but for u it's negative beta x, which is right there. Du is negative beta dx. We have a beta dx. We need a negative one, so we need a negative in there. And so I'm just going to, this beta, I'm going to put this beta over here next to the dx. And I'm going to put, I need a negative 1 there, so I'm going to multiply by negative 1 on the inside, and I'm going to multiply by negative 1 on the outside. Multiplying by negative 1 twice is the same as multiplying by 1, which doesn't change the value of anything of this. So we have a negative beta dx here, which is du. So now after we substitute, we get the above, which was this, right? So that's this, except now negative beta dx is du. Negative beta dx is du. And when x is 0, u is 0. So that stays 0. When x is infinity, then u is negative beta infinity, which means this is negative infinity. And so now this is equal to the integral. If you negate this, you switch the limits of integration. So it's the integral from negative infinity to 0, switching the limits of integration, getting rid of the negative sign of e to the u du. And so this is equal to e to the u evaluated from 0 to negative, evaluated from negative infinity to 0. And so this is just e to the 0 minus e to the negative infinity. And this is equal to 1 minus 0, which is 1. Okay, and so the expected value is 1. Okay, and so that's the answer. And so now if you, right, so I have an answer sheet also. Let me just find it. It's next to the practice questions. Okay, here, so then, oh wait, it's 1 over beta. Oh wait, there's, oh, okay, I fixed, hold on. Here, that's fine. E of x, sorry, it's x times f of x, which is this. Okay, so you have, okay, so let me just fix it. Okay, so you're integrating x f of x, which is x times beta x, beta e negative beta x dx. Okay, so it's not use substitution. You're going to use integration by parts. Okay, so use integration by parts to evaluate. Okay, so we can let u equal to x, and dv is equal to beta e to the negative beta x dx. And so that implies or means that implies that du equals dx, and that v is equal to the integral of this antiderivative of this, which is then equal to negative e to the negative beta x. Find a derivative, you get that. Okay, so that's v, and so that means the above equals. Okay, so this is uv. This is uv minus the integral of v du, and it's going from when x is 0 to x is infinity. Okay, and so now this is equal to u, which is x, times v, which is this, evaluated when from x is 0 to x is infinity, uv minus the integral of v, which is this, du, dx, evaluate from 0 to infinity for x. This is equal to, well, so this expression here is the same as x divided by e to the negative beta x with a negative sign in front. Let me just put a -1 there. So it's equal to the negative of that, right? Evaluated from 0 to infinity, right? Now it's minus minus. This is plus this integral without the minus sign. Okay, and so when you calculate this, then when you take the limit. Oh wait, it's wait. It's a negative e to negative beta x, which means it's e to beta x in the denominator. So the denominator goes to infinity much faster than the numerator. So when you plug in x is infinity, this is 0. When you plug in x is 0, it's also 0. So this expression is kind of like -0 plus 0. Okay, so it's -0 minus -0, which is plus 0. So you get something like that. And so that goes away. And then now you have this integral. And so when you use substitution on this, you get 1 over negative 1 over beta times e to the negative beta x. This is evaluating an integral and evaluating that indefinite integral. And so you evaluate this from 0 to infinity, and then this is equal to the 0, doesn't matter. So now when you plug in infinity, you get this expression when x is infinity, which is the same as -1 over -1 over beta times e the beta x when at the point where x is infinity, meaning plugging infinity. And so this is 0. And then minus the same expression, except when x is 0. Okay, and so the first expression becomes 0, and it's minus, which is a plus. And when you plug in x is 0, you get 1 over beta. This is equal to 1 over beta. There we go. So that's the answer. Okay, so when you look at this over, I'm doing these calculations, and so you use integration by parts, and you evaluate that e of x is equal to 1 over beta. Okay. Okay, so it's 1 over beta. Okay, so that's number 6. E of x is 1 over beta. Okay, so that's 7 and 6. Okay, so you could just look at the. So I wrote. I'll also accept this answer. It's a simplified version of that problem. I gave another. I accept 2 answers to that problem. I gave the second one. Okay, so 5. Okay, so any other questions from the review sheet? So I didn't make a review video for homework 11. I typed up all the solutions and I have it on Blackboard. And I have an office hour tomorrow. So if you have questions about it, I'm happy to go through it with you during the office hour tomorrow night. Okay, so you should do the homework first tomorrow, earlier in the day. And if you have questions about it, I can answer them for you during the office hour tomorrow. The integrals, so I think you mean like if you just have this, right? That's not a final answer, right? So you have to evaluate that. So e of x is equal to that, but you have to evaluate it and find it's 1 over beta to get full credit. Okay. Okay, so I guess we're out of time. So again, I have office hour tomorrow. So if you have more questions, you can come to office hour and I'll help you there. Okay. The test again is this Thursday, right? So the second exam is December 9th. This Thursday, that's the last day of class. And the final for this class is on December 21st from 6:15 p.m. to 8:15 p.m. Okay. So I recorded this lesson. I'm now stopping the recording.